from University of Greenwich. Steve has been a senior research fellow here since 2001, before which he had completed his thesis relating to human egress. His interests rely on a multidisciplinary approach to understanding emergency and non-emergency egress behaviour in a variety of environments. During his time here, he's been actively involved in research, design and implementation of the various forms of exodus, the air, building, maritime and rail. And in addition, he's been heavily involved in practical engineering applications of these models, as well as being involved in the design, performance and management of numerous evacuation experimental trials. Steve.
Okay, thanks. Hello to everyone in the room and outside in the ether. I haven't heard anyone say that yet. So, well, I'm Dr Gwynne. I work here at Greenwich in the Fire Safety Engineering Group. Today I'm going to be speaking about validating the buildingEXODUS model using data that we collected from an unannounced trial evacuation, and then using the model to examine the procedures applied within the structure. Before I start, I'd like to acknowledge my co-authors, especially Jason Park, who's been sitting up here most of the week, for the data collection, the analysis and the simulation process. I'm going to briefly discuss the importance of pre-evacuation times upon the overall evacuation process, then discuss the data that we collected very briefly, and then the use of this data, the dreadnought data as I refer to it, within the buildingEXODUS model as a means of verification, then the use of the model to investigate the procedures applied within the dreadnought structure, and then I'll make some concluding remarks. Over the past 2 decades, the evacuation modelling process has emerged as a valuable and viable means in which to investigate the egress capability of structures and the processes that emerge during an evacuation. However, the development of these models are highly dependent upon the availability of data and the suitability of that data. The majority of data collected tends to be either from evacuation trials, which may have been designed to examine specifically the performance of an individual structure, or from actual incidents where there may be omissions in the data collected, or the reports actually being based on anecdotal reports of those involved. In both cases, the interests of the people collecting the data may not necessarily coincide with those building evacuation models or those using evacuation models. This presentation, therefore, relates on the collection of pre-evacuation times produced during an unannounced evacuation trial at a university facility here at Greenwich, and the use of this data within the buildingEXODUS model. This data has been collected in a format so that it can be used both in the evacuation modelling environment and as well as being used, hopefully of use to the general research community. During this presentation, I'll be using the term pre-evacuation time to refer to the time after the sounding of the alarm bell to the time just before an individual makes a purposive movement to evacuate. We're not using the term pre-movement time, as that can sometimes cause confusion, as within this period of time people may be actually moving but not evacuating. The structure we're looking at was a 3-storey structure with approximately 3,000 metres squared of usable space. It was a reasonably complex structure built up of library facilities and computational laboratories. It had 6 stairways and 8 exits available to those during the evacuation. Here in red we see the 2 exits that were used primarily during normal circulation, and the exit that would have been used in normal entering and leaving the structure. This is actually quite important when we look at the procedural analysis later on. During the evacuation, a traditional bell system was used and was supported by staff who encouraged people to evacuate and then guided them or attempted to guide them to use specific staircases and specific exits. It was very important to us that the population was previously unaware of the evacuation and the fact that it was actually a drill. Obviously this would have had an impact upon the results collected. You can also see the relative complexity of the structure on the ground floor, the first floor and on the top floor, and it's actually quite similar in design to this structure here and in the nature of the complexity. What we did during the actual trial was to secrete 15 members of research staff around the structure in a fairly unobtrusive manner so that people didn't actually see them until they'd left the building. This enabled us to collect data on the number of people using each exit and the arrival time of each individual as they arrived at the exit, enabling us to establish these distributions. Again, this will be quite important for the later analysis. We also had access to 62 closed-circuit TV cameras, which the people in the structure would have been used to, so they wouldn't have been seen as an indication of a recording device. And this enabled us to collect the pre-evacuation times of the individuals involved. So in total, 359 evacuees were recorded at the external exits, and 247 of these had their pre-evacuation times recorded via the CCTV. Questionnaires were also distributed at the end of the evacuation, just to gauge some of the experience of those involved and enabling us to analyse compare the results produced in the model with those produced during the evacuation trial in terms of both qualitative and quantitative aspects. To analyse the closed-circuit TV data, a template was produced, enabling us both to analyse the times that were taken to respond and also the reasons behind those times, enabling us to get a much more detailed picture of what actually was going on. So here we have one form of the analysis. Here we just have the pre-evacuation times of every individual that was recorded. And here we've separated this out according to role. Now this is just one means by which we separated the data out. We also looked at the reasons that people responded. For instance, were they prompted, were they alone, what they were doing, the number of actions they performed prior to their response. And this gave us a much richer understanding of the response process and made better use of the data. Here you can see, for instance, although there are relatively few members of staff within the structure, the range of the responses involved are actually about the same as the students. Here in this schematic, what we've got is we're trying to represent the pre-evacuation times according to location. And again, this will be quite important in the simulations we're using. So here we can see the pre-evacuation times according to each of the rooms within the structure. Those that are in close proximity to each other tend to have relatively similar pre-evacuation times, while those that are isolated may have extended pre-evacuation times, maybe due to the fact that staff took time to get there or because there was no reinforcement of the cues received. So as I said, the arrival time of each individual was recorded at the exits, enabling us to establish an evacuation curve. Here we can see the exits that were used during the evacuation, the total number of people out, and the time of the last person out, and we have the arrival times of each individual here. You can see here that the two exits that are mainly used during the evacuation were two side exits that were not previously part of the circulation usage of the structure. This was entirely due to staff guiding people to use these exits and was therefore as a result of the procedures employed. The overall time to evacuate the structure was 313 seconds. So here we have the frequency distribution of the pre-evacuation times recorded during this evacuation. And here we have the frequency distribution of the total evacuation times. And you obviously have a time shift along the axis. And this is similar to times that were also recorded, a similar pattern to the times recorded by PERSA and the University of Ulster in an examination of pre-evacuation times in a different structure. But it's a similar pattern if the numbers are actually slightly different. Now this type of data is particularly useful for models because firstly it describes the pre-evacuation times in some detail, and it also then allows you to compare the final results produced with an accurate representation of the overall evacuation time, so it's particularly useful for validation. I'm going to be using the EXODUS model here. I'm sure you're familiar with it by now. It's able to represent the impact of people, fire, and the geometry itself, and is a rule-based model. I won't go into this in too much detail because we've heard about this previously. I'll be looking at 6 different scenarios, 4 specifically aimed at validation and 2 aimed at investigation. The 2 factors that I'll be looking at is varying the pre-evacuation times employed within the model and the exit usage. So in the first 2 scenarios, I'll assume that the evacuees respond instantly, whilst changing the exit usage within the simulation from assuming that people use the nearest exit to approximating the exit usage during the actual trial. I'll then go on to apply the pre-evacuation times collected at different degrees of accuracy. So in scenario 3, I'll apply the range across the structure. So this might be what might be expected if we were doing this type of this simulation if we just had the pre-evacuation times and didn't have location-specific data. In scenario 4, I'll be applying the pre-evacuation times according to the rooms, not on an individual basis, but according to the rooms within which the individual started. And this can have quite an important effect. As you can see here, we have the evacuation times across the structure and the variation between the rooms.